Good morning, good afternoon, everyone. Thanks for joining the Cognitive Systems Institute Group Speaker Series. Today I am pleased to announce Dr. Ching-huei Tsou, a senior software engineer in the Watson Algorithms Group from IBM Watson Research. His areas of specialty include machine learning, numerical optimization, and software engineering. Dr. Tsou joined the Watson Research team in 2012 after Watson won the Jeopardy TV show, after which doctors were most interested in seeing how Watson could help in the healthcare domain. He is the research and technical lead of the Electronic Medical Records Analysis Project in IBM Watson. Dr. Tsou holds a PhD and a master's in engineering from MIT and a bachelor's from National Taiwan University. Today, Dr. Tsou is going to be presenting towards generating domain-specific, personalized problem lists from electronic medical records. Thank you, Ching-huei, for being here, and I will turn it over to you.
Okay, thanks. Hi, everyone. Given this is a short talk, I'll just jump right into today's topic. This is a very exciting area, and today I will focus more on one very specific area, which is how to generate a problem-oriented summary from the EMR. And this, as you will soon see, this plays an important role in the overall roadmap we are trying to do here. So all this started from Watson's post-Jeopardy challenge. Because after the Jeopardy success, it's obvious we want to do more than a TV show challenge. And our first domain of exploration is the medical decision support because of its mature and complex and meaningful nature. Something happens a lot is after people watch the Jeopardy game and they think Watson can answer pretty much any questions, and they just assume, especially people that are outside of the computer science community, they just assume that anything that could be phrased as a question could be answered by Watson. So people often ask, can you do this, Watson? Give my medical record, and here is the hundreds of pages of structured and unstructured data. Can you figure out what's wrong with me? Obviously, we are still a long way from there. However, we accept this challenge, and we propose building a cognitive assistant, which together with a physician can better answer this type of question. So here you see is the overall roadmap, at least in our group, of what we are thinking of applying Watson to build this clinical decision support system. So here I will just give you a real use case we are working on, and you will have a better understanding of how this is supposed to work. So the first thing is what we want to look at. We want Watson to look at the EMR and to summarize that, and show the summary UI to the physician. So from the summary UI, the physician can spot something that's not right. For example, he or she noticed that the patient's creatinine level is high. And once that's clear, the next thing is the doctor may want to know what is the cause of creatinine elevation. So this is general medical knowledge and independent of the EMR. The doctor most likely knows most of it, but there's always something new, and it's very hard to extract all the new information. So Watson can help there to extract all the medical knowledge from published articles. And from there, the next step is the doctor will naturally want to know which one of this applies to my patient. So there are a lot of potential causes, but not all of them are related to my patient. So Watson will need to do some reasoning and find the most likely cause for this patient. So this, again, relies on Watson combining the medical knowledge and the data extracted from the EMR. So the next step is we want to build this EMR QA systems so there many more sophisticated questions can be asked and answered. Something like what has been done in the past, and what else can I try? What works and what does not work, and why? Okay, so today's topic will be focusing on the first part, where we want to extract useful information from EMR. And that's the foundation of many of the other things we want to build. So I'm not sure how familiar you are with a electronic medical record, but basically it's a lot of structured data and unstructured data. Structured data like diagnosis and medications and lab test results, they are stored as tables in the EMR systems. And there are, on the other hand, there are a lot of those unstructured data, which are the clinical notes. Typically, a patient has about hundreds of those notes, and for an older and maybe sicker inpatient a patient, they will have a lot more, sometimes thousands or even tens of thousands. And there are many, many useful information embedded in those unstructured data. And this is where we want Watson to. This is where Watson shines, because it's good at reading those unstructured data. So almost all large hospitals in the U.S. has moved from paper records to EMRs. And as you can see from this slide, there are a lot of promised benefits of EMRs. So something like reduce the paperwork and increase the patient care. I got the two pictures on the left from a Cleveland Clinic doctor. He said this is why he went to the medicine, and the one below is definitely not why he went into medicine. So there are these great promises of EMRs. And are we getting all this benefit today? The answer is probably no, because I also get these slides from the same doctor, and he said today's medical record is a lot billing oriented. So if you look at the table below, if a patient has a heart failure or congestive heart failure, a doctor really want to know is the one on the left. Probably only one of them is good enough. But in order to get paid for all the procedures done, they have to document all this additional code. And to qualify for each of this code, you also need to document all the evidence and procedures and things that you have done. So the clinical notes is bloated with all those additional billing-related information. And the meat is just buried there and very difficult to find out. So it is important to create a summary to summarize what's actually going on with the patient. Consider that the physician who is about to see a patient, before seeing the patient, he or she needs to prepare for that. And a lot of times they want to know what is the current problem, and what was the problem last discussed, addressed, and how is that problem being managed? What are the medications the patient is on, and what are the lab test results that's related to that problem? So you can see that many of these questions are problem-oriented. So the idea is we want to create a problem-oriented medical record summary. The whole idea is not new. It's actually proposed by Dr. Lawrence Weed in the 60s. And this is used by most hospitals as the official record-keeping method. And it's also required by HL7 CDA. And the key of this is you can see that the problem list plays a central role. And if you're interested in certain problem, you want to start from that. And from that, you want to see all the related procedures, vitals, lab tests, so on and so forth. And also the clinical notes where it's been discussed. So the key of this is to have an accurate problem list. However, the problem list today is manually maintained. So after a visit, a doctor is supposed to update that problem list. But as you can see, a patient sees more than one doctor. So the problem list is, in fact, a multi-author document. And even though it's mandatory, not every doctors pay the same amount of attention to that. And over time, is often dated with incorrect information. In fact, we tried this with many of the Cleveland Clinic EMRs, and we created ground truth, which indicates what are the real problems of this patient, and compare the ground truth with the existing problem list in the system. And we find out the existing problem list is not doing a good job. Many things are missed, and there are many things that's already resolved, or something that's acute, or some rule-out diagnosis. They are still on the list, and that becomes very confusing because that renders the problem list useless, because there's no way to know which one is still active and which one is already resolved. And things like some pre-existing problems, maybe no one has the time to update that and doesn't show up on the problem list. So all this make the problem-oriented scenario hard to do. So the idea here is, instead of asking the physicians to update the problem list, we want to ask Watson to go through all the clinical notes, the structured and unstructured data, and to create those problem lists for the physicians. Before we do that, the problem list is the definition of what is the problem. We often get this question, what is the problem? And the definition is actually very vague. It's basically a list of anything that's important to the patient care. So as you can imagine, this is a good candidate for a machine learning technique because it's very hard to build any rule for that. So the best way to do this is learning from examples. And here is, this is not meant for you to read. This is to show you that in order to do a machine learning, we are using a supervised machine learning at this stage. In order to do this, we need ground truth. We need the labels for those training examples. So we ask annotators. We give them. We work with medical doctors to create this guideline to tell our human annotators, which are fourth-year medicine students, and what should be considered as a problem. As you can see, that those are still very long and subject to explanation. And also, we give examples here. A human will have enough medical knowledge in order to apply this and create the ground truth. So we gave this to 2 human annotators, and they will independently annotate an EMR and then adjudicate the result with the MD. So we use that as the ground truth to train Watson. So at a very, very high level, the problem list generation has 2 stages. The first stage is we want Watson to look at all the clinical notes and find everything that looks like a problem and use that as the candidate. And the second stage is to, again, scan through all the structured data and unstructured data and find evidence to support each candidate and use those evidence to rank those candidates. And at the end, we will have a ranked problem, and we will use that as our problem list. So here is the example of a clinical notes. As you can see that they are very dense, and you see that name AAA, BBB is because those are de-identified. We are not supposed to see those real nodes. Those are real nodes. We are not supposed to identify the patient's identity. So every EMR has to be de-identified. And it's very dense, and there's no formal structure. You can see there's S and O. S stands for subjective, and O stands for objective. So Watson needs to understand that in order to make sense of the document. And there are many, many shorthands and abbreviations, and it's very dense, and it's not, there are very few well-written structures. It's more like a brain dump. So we use many of this. As I said before, a patient, one EMR may have hundreds of this, and Watson will need to go through this. So this is what Watson's understanding of these nodes. So we identify all those named entities and link that to the UMLS, which is the Unified Medical Language System created by National Library of Medicine. It is a curated taxonomy. We link all those medical terms to a concept in that dictionary, so we understand the entities in here. So on top of that, we also need to do some assertion detection, like negation. If a disease is mentioned as negated, we care less about that. And we also need to know some other assertions like family history, or is this just a hypothetical rule out thing, or this is a real problem of the patient. So in addition to entity linking, we also need to make sense of in what context those medical terms are used. As you can imagine, this is not much different than any other context of where computing, where, if you can see in these examples, the cat in the hat, those A and H, they are exactly the same, but for humans, there's no problem to understand this. And another example is this A, B, C, and 12, 13, 14 on the right. The B and 13 are exactly the same, but given the context, you understand the meaning. So the key is, what is the context in terms of a EMR? So if you see, like I said, the first step is to do entity linking. So you see the word hypertension or HTN in the notes, and you know that it's hypertension. So you get a small confidence that the patient may have something to do with hypertension. But then you expand that, you look at the sentence level, there's something like hypertension, yes, then, well, it's stronger evidence that the patient may have hypertension. And you look further and see this sentence is mentioned in a assessment and plan section, then, well, pretty much this is a real problem. And then you look at other nodes and align those nodes with the medication lab test result, and you see there are some active medication that's being prescribed to treat hypertension. Then you are pretty confident this is the real thing. And then you combine this with all the training examples and other EMRs, you can recognize a pattern. So this is, at a high level, how we generate a problem list. So this picture just summarizes what I just described. So we start from EMR and we do the candidate generation. And there are many, many things we do to extract those evidence and score them. And at the end, we put them all together to generate this problem list. And we are doing at this point, we are still improving a lot of the things, but we have some tests done with the clinic plan clinic physicians. And so far, our accuracy is much higher than what's already there. So I will show you how this works. This is the UI we created, and you can see that on the left-hand side, this is the problem list generated by Watson automatically, which summarize the patient's important issues. And Watson also groups related things together, so this will help the doctors to reduce their cognitive load. And if you are interested in certain problems, you can just select that. And once you click on something, you can see that the related medications is being highlighted, and the related lab tests is also highlighted. And on the right-hand side, all the nodes this problem are discussed is also highlighted. So you can easily go from a problem to the related medication as nodes that's discussing this issue. So there's just further examples. You can use the UI and drill down and find all the related issues. So you start from diabetes, and you can look at the related lab tests like A1C, and it goes down and goes up and down. And you can easily click on that. It will take you to the action nodes that's discussed, and you can see that why or something goes up and down. So also we do something semantic find, because not everything is a active problem that need to be on the problem list. So sometimes you want to see if the patient ever has something that's not listed. You can do a search. And on top of the literal match, we also do semantic match. So in here you can see that if you type in something like healing problem, Watson understand that is a medical concept and try to map that at a medical concept level. So you can see that we found no healing loss and as a match to that. And also we find this mid-ear infection may be related to healing problem. And also we find related medications that's used to treat mid-ear infections. So all these are connected at the semantic level. So so I think I will briefly go through these challenges and stop here, because this is a product for IBM, and this is also a very exciting new area. We have been spending a lot of time and resource, and a lot of that because there are many challenges ahead. Maybe this is more to the interest of this group. The first thing is we have this data issue, because currently we have about 1,000 EMRs from Cleveland Clinic. And because the EMRs has this PHI information, they have to be de-identified, which is a time-consuming process. And it's also error-prone, because sometimes we get an EMR that's supposed to be de-identified, and we spend time and energy to analyze that. And in the process, we notice something that can be used to identify the patient. So we have to inform the hospital, and they will recode that EMR, and we cannot use that EMR anymore. And the ground truth also needs to be generated, adjudicated, and vetted manually. That's also a slow process. So we are doing many things in order to improve that. Things like we are creating a HIPAA-compliant environment where we can host the EMRs there, and they don't need to be de-identified. And we are also doing this unsupervised pre-training and feature selection, so we can do some pre-training which does not require ground truth. And we also want to do active learning. We want to deploy this to the hospitals and collect user feedbacks and use that instead of creating the ground truth ourselves. And there are also many natural language processing issues, because clinical notes, like I said, they don't have time to write a well-written, structured article. It's just a brain dump at the moment. So a lot of the existing parsing, negation detection techniques doesn't work very well out of the box. We have to do a lot of shallow parsing and to detect the sentence boundary differently. And there are many abbreviation expansions that's not usually used in daily English. And relation detection, things like what is the problem, what are the comorbidity of the problem, what is the medication that may be used to treat these problems. Those evidence, we also need to learn that. And last but not least, we trying to improve the accuracy. Like I said, this is already doing a much better job than the existing system where the records are kept manually. But we still want to improve that. We want to merge some of the problems, like if there's a finding, which is a finding of another disorder, which is already on the list, you don't want to show both because that's redundant. But these two are not really the same thing. One is a finding, one is a disorder. How do you know they are the same? They are related. We need to know that and combine the two. And also there are transient problems, something that has been true for many years and has very strong evidence throughout the EMR, but after surgery or a recent event, it's been resolved. It's very hard to detect a major change at one point. So those are the challenges we are facing, and hopefully this will give you some ideas of what's been worked on and what are the other research areas you may also want to participate. Okay, so I will stop here and see if you have any questions.
Thank you, Ching-huei. This is fascinating. Let me open it up for questions and ask the audience, if you're on the phone, to press *1 to unmute your phone, or if you're listening through your computer, to press the microphone button to unmute at the top of your screen. Are there questions for Ching-huei? Ching-huei, this is Diane. I have a question.
Yeah.
How difficult is it, once Watson determines, what should be in the problem statement, how difficult is it to train Watson, to remove something or change something?
Yeah, it has 2 steps. I actually have that in this deck. So it has 2 steps because the system is used by more than one doctor. So if a doctor chooses to remove that, maybe it's just his or her personal preference. So if he, in the UI, will collect that feedback, and if you choose to remove this, next time when you log in, you won't see that anymore. So it's done, it's gone. But other doctors may still see that. So Watson will accumulate that information. And once we have enough, we will retrain Watson automatically. And if many doctors say this is really something wrong, and Watson will learn to remove that, and it will be removed from the system, and no one will see that. So the impact is immediate for the direct user, and has to be accumulated over time for the entire group of users.
Hi, Diane. This is Paul Courtney. I have a question.
Yeah.
Sure.
Hi. Yeah, I'm curious about when you were putting this together, what was the tooling that you used for the annotation, and then what parts of Watson did you interact with? What systems were made available?
I'm working with I joined the original Jeopardy team, and the whole thing is built on top of the UEMA, and many of the Watson MD components that's built on top of that. So the NLP stack is from the Jeopardy days with some customization, and we call that the Watson MD core, and we use that to annotate the notes. And after that, all the annotators are also built as the UEMA annotation. And we created a pipeline on top of the NLP stack, which analyzes the EMRs and do the machine learning there.
Okay, great, thanks.
My name is Martin Apple. Can you hear me?
Yes.
Yes, Martin.
So my fundamental looking at this is that what you're trying to do is use a lot of language recognition to do something that I'm not sure is the major medical purpose of this. You're trying, essentially, the most important thing you're going to do with the patient is get a proper diagnosis. You have to separate out symptoms, figure out what was the fundamental causes of those symptoms. Once you've got that clear and verified, and you do that by eliminating possibilities that could be the possible options, your next step is pretty well taken care of, because there's only so many ways that are acceptable to do various kinds of treatments. That's the simple backbone on which, if this was built that way, you could probably zero in quickly on why all of these language things are happening, why these notes are being put down, and so forth. But to try and work it from the other end, from collecting all the verbal data and trying to put it back together without some kind of fundamental framework like this, seems to me it's going to take a very long time.
Right. There are actually 2 different projects. In here, we are doing one way. We are doing from the bottom up. We are trying to find everything. So this is not reasoning yet. We are just trying to extract information. And there's very few medical models used here. So this is just to summarize. So actually, we don't do any diagnosis here. This is just to summarize. If we want to say something, it has to be documented by someone somewhere, and the task here is to find it. And the next step is, like you said, we want to do reasoning, we want to do diagnosis. that will take this as the input, and also that will take medical knowledge, those models created somewhere, as the input, and combine the two to do the reasoning. Of course, if we use those models, it will give us some advantage because the model tells you what are relevant. You only need to focus on those. So these two actually go hand to hand together. But today's talk, this part is just the summarization part. Like you say, it's from the bottom up. It's very noisy. I totally agree on that. And there are a lot of work need to be done without using a medical
society.
model.
We at ACS are committed to improving people's lives through the
I'm not sure what that was, but thank you for your questions, audience. And let me just thank Ching-huei for being our presenter. I thought this was fascinating, and I will post a recording on our website. Thank you, audience, for joining and for your questions, and we'll see you next week.
Thanks, Diana. Bye.
Bye.